So I think I might get started then. I'd like to start the webinar by acknowledging the traditional custodians on the lands on which all of us here today live and work. I acknowledge the value of their traditional knowledge, which really I think tells really powerful stories about our weather, the climate and its current and future impacts on our ecosystems and environments and species that live there. So I pay respect to their elders past, present and emerging. As I said before, this is the first webinar in the Climate Matters webinar series. The webinar today will be focusing on Australia's climate changing extremes and hazards. We have two presenters today, Lead Chief Investigator Dr. Cathy McInnes and Julian O'Grady, both from the CSIRO Climate Science Centre. Cathy and Julian have contributed to the Hub projects which focus on marine and coastal climate services for extremes information. So I think we'll get stuck straight in and I'll pass over to Cathy to start your presentation. Thank you, Cathy.
Thank you very much, Sonia. Yes, so Julian and I are going to be highlighting the work we've been doing in Project 5.8 to understand changing coastal hazards. So I'm going to start with a bit of an overview of the breadth of the work that we've been doing in the coastal space, and then Julian's going to finish with a demonstration of our main sort of tools that we've been developing to try and disseminate the information to our next and end users. So in our project, our challenge is really around how marine and coastal extremes are changing now and into the future. And the context of this, of course, is Australia's very much a coastal nation with much of over 80% of our coastal population living within about 50 kilometres of the coast, and extreme exposure, about 226 billion based on 2008 dollars in infrastructure that's exposed to a 1.1 metre sea level rise. In addition to that, of course, is the marine biodiversity. So we have a very extensive coastline and much of our biodiversity is being challenged by increasing temperatures in the ocean and acidification and so on. And industries such as fisheries and aquaculture are also at risk. So our project is really focused on understanding changes and understanding the changes and future projections of sea levels, waves and coastal extremes, including marine heat waves, as well as other facets of these processes, such as how do they respond to interannual variability and so on. So understanding the dynamics that drive extremes in the coastal space. And we're also sort of focusing on developing improved ways to deliver the information on coastal change to stakeholders through improved climate services. So that's the other sort of area of work that we've been focusing a little bit on in this phase. So, sorry. So how we addressed the challenge was really to sort of break the work into 4 general areas. The first was focused on building knowledge and tools. So this is the sort of underpinning science, the peer-reviewed papers that focus on the different topics, waves, extreme sea levels, hydrodynamics, marine heat waves and so on. During this phase of NESP 5.8, I think I counted about 16 peer-reviewed papers that have been put out by various researchers across our project. And the other part of building knowledge and tools is on enhancing features in our website, which is the link shown there, as well as the Canute 3 sea level simulator, which Julian's going to introduce you to later on in the talk. In terms of our stakeholders, a big focus in this phase was to really understand their needs. And we decided that because there's really a wealth of information out there already, rather than dragging a bunch of stakeholders to the table to tell us what they want, we felt that a very useful starting point was to really review what's available both here and internationally in terms of stakeholder needs. There's been work done in Europe and so on that we could tap into to better understand stakeholder needs, and also the state of climate tools that are available both here in comparison to what's available overseas. So our literature review sort of focused on those 2 facets, but I'll talk more about that in a moment. We also, as part of Hub activities, have strong international engagement, primarily through the World Climate Research program Grand Challenge on sea level rise, which also has its goal better understanding stakeholder needs and building climate services. So, you know, we have a strong linkage into the international community through that activity, and also the Coordinated Ocean Wave Climate Into Comparison program, or COWCLIP, which is really harnessing international effort to bring to bear on understanding wave climate change because of the sort of enormity of the problem and the need to collaborate extensively internationally to really pin down sort of answers on how wave climate is changing in the future. So as a result of our deep dive into what we believe stakeholders need and what they have or don't have, we also then went on to deliver some climate, a compendium of 6 different climate briefs and fact sheets, which really highlight some of the information that we felt we can start to contribute, but particularly if we're sort of thinking around new climate projections. These are different ways in which we can present information that may resonate more with the end users that may be using the information, and I'll talk more about them later as well. As I said, there were 6, 2 focused on marine heat waves, 1 on sea level rise, 1 on extreme sea levels, coastal wave climate change and offshore waves. We also collaborated with other projects in the Earth System Climate Change Hub and developed some collaborative or contributed to some collaborative papers on various topics. And again, I'll mention those in more detail later. Okay, so I'm going to talk now about the science that we've done, which has, and I'm not going to talk about all the science we've done. I've just picked 4 different highlights, just 4 different examples just to talk about here. So we've continued our activity, which is to maintain how sea levels are changing based on satellite altimetry. So this is sort of an activity in which we keep updating our tide gauge sea level reconstruction and also downloading, quality controlling, processing satellite altimetry sea levels. So we can produce information such as shown in the figure on the right, which helps us to monitor how sea levels are changing. The figure on the right is actually the one that was prepared for the State of the Climate report, but we also have this information on our webpage as well. And what it's highlighting is that over the 20th century, where we had an average rate of rise of about 1.5 centimetres per decade, in the satellite altimetry period, the orange curve at the end of at the right of the plot, that rate of rise has increased to around about 3.5 centimetres per decade. So this sort of activity is just maintaining and keeping a watch on how sea levels are changing or trends are changing globally. The second piece of science that I just wanted to touch on is just a paper from the marine heatwave area of work, and this one's really examining what are the mechanisms that cause marine heat waves. And so this is just a nice little study with a key figure on the right showing all the different mechanisms that can contribute to enhanced marine heat waves in the area, and it includes things like climate drivers such as ENSO, Madden-Julian oscillation, interdecadal Pacific oscillation and so on, which can help to make conditions more or less conducive to marine heat waves. It also links in the role of warm currents in contributing warm water into an area to increase the chances of marine heat waves occurring, and even weather conditions. So blocking highs, for example, can lead to prolonged periods of very clear weather where solar radiation can penetrate the surface ocean and contribute to marine heat waves. So that's an example of one of the papers that's come out of the marine heat wave area. There's been also a lot of work done on understanding ocean waves, and this particular study that I've just picked here is one that's looking at where waves originate from and how they impact other parts of the global ocean. So it's highlighting waves in the north, from the northern hemisphere, in the tropics from the northeasterly trade winds, the areas shown in green. Sorry, I've got a pointer here. Southeasterly trades, Asian monsoon, which affects this area up here, and the southern southern hemisphere wave swell, which really is very significant for the Australian coastline, as you can see, affecting at least half of the continent. And so that's just sort of a nice example of how far afield, particularly long period swell waves, can penetrate into other ocean areas. And it's particularly significant for the Pacific Islands that can cop it from both hemispheres as well as locally, but also around the Australian coastline as well. And then the final study I wanted to just highlight is some work that contributes to our understanding of extremes around Australia. So, for example, we've had a good idea now from previous NESP work that where our storm tides maximise around the coastline. So this is storm surge plus tide in a probabilistic way. So this is a 1 in 100 year event showing that highest storm tides occur off the north west shelf in Australia, relatively more moderate values. The key to understanding the colours is over here on the right, around the rest of the coastline. But of course, extreme sea levels are not just storm surge and tide, but also waves, particularly waves from the south, as I'll show in a sec, contribute to the mean sea level or the extreme sea levels that occur during one of these severe weather events through wave setup. And of course, that was the part that was missing in this figure. So one of the studies that we've published in this phase was to understand how wave setup relates around the coast, a 1 in 100 year wave setup event. And we can combine these two so that now we've got total water level that includes not just the storm surge and the tides, but also the wave setup. So we get this total water level picture around the coastline. And this was an important piece of work to help us enhance the Canute sea level tool to include wave setup, which Julian will talk about later. And again, you can sort of see a much more different picture because wave setup is somewhat more pronounced along the southern coastline, where we have this strong influence of the Southern Ocean swell affecting the coastline. Okay, so that's a little bit just a snapshot of 4 studies that were undertaken in the sciencey area of our project. The other piece of work that we focused on was our literature review. And as I said, we focused on 3 kind of different sectors. So traditionally, we've focused on coastal services for land management, planning and adaptation. So this is sort of like the infrastructure, where people live, you know, the coastline, the beaches we like to go to and so on. And so sea level rise is a key piece of information to inform planning in that area. We also reviewed, and that was the most widely available. We also found that while extreme sea level information was desired, it was less available in a, you know, sort of to the entire community. I mean, there are obviously very targeted locations that are rich in information, but in terms of a general service for Australia, that was lacking. That kind of links back to, you know, what we've been trying to do with Canute, but also we found that whilst tools and services delivering sea level rise were well serviced in Australia, we have Coast Adapt, we have the Climate Change in Australia tool, tools and services delivering extreme sea levels were less prevalent. And again, this harks back to a focus on Canute. In the marine services for aquaculture, fisheries and management, we've sort of found from our review that the priority so far has really been around understanding the physical processes at high resolution. And again, harks back to the study to better quantify, you know, what are the different mechanisms that contribute to marine heat waves. And the tools and services are somewhat limited, and if we think about sort of sea surface temperature information, that's tended to be, for example, through climate change in Australia, that's tended to focus on changes to mean conditions rather than extreme conditions. Hence our focus here on building up more information on extreme heat waves and the way we can deliver information on extreme heat waves for the future. And finally, the marine services for maritime and offshore industries. Their focus has typically not been on climate change scales, although that may be changing, particularly on the sort of more near-term time horizons, but their main focus has been more on met-ocean variables such as winds, waves and currents, and really more focused around servicing of their offshore assets. So, for example, you know, they're very interested in periods of calm weather because that's when they can get out to their do their servicing and get out to their offshore rigs and place and things like that. But climate change on the sort of more nearer term time scales is becoming increasingly relevant. So that's sort of an opportunity to try and, you know, target them with information that's more useful to their needs. So on the back of the findings of that review, we then spent some time developing up some this sort of series of climate briefs and fact sheets to better target some and provide some demonstration of the way we can present information that may resonate more with those different sectors or you know, stakeholders in those different sectors. And the first two are two fact sheets on marine heat waves. So what they're focused on is the weather and the ocean factors that contributed to marine heat waves, the impacts of some very significant past marine heat waves on the biodiversity and fisheries, and then focused on how temperature changes projected for the future will alter the events in terms of their frequency, intensity, and duration. So I'm just starting with some figures from a case study in the West. This is the so-called Ningalo-Nina event. This was a really significant marine heat wave, most intense in 140 years of record. It impacted over 2,000 kilometres of the coast, and it led to waters above 2 to 4 degrees above average conditions for over, I'm just trying to recall, for over 10 weeks along this sort of section of coastline. It had significant impacts on industries such as clams and crabs, or I believe, and also it devastated seagrass meadows in the region, and some species in the area have become locally extinct since that event. So what's been focused on here is ways of presenting information. So this is the 2011 event, very much an outlier in the historical record, where you can, although there are a few other extreme events in there. But what this is looking at is, well, under two different emission scenarios in the future, how unusual will this event be in terms of its intensity? And as we can see, if we continue on a low emissions trajectory, it'll remain a rare event and an outlier. But unfortunately, if we progress along a high emissions scenario, this starts to become quite a common occurrence. Similarly, in terms of marine heat wave days per year, as I said, I think it's about 200 days per year in that particular event, but under a high emissions scenario, it's in every day of the year. You know, it just becomes the normal conditions. Under low emissions, you know, it still remains roughly, you know, the same number of days per year. And in terms of return period, that particular event was around a 1 in 80-year event, but under high emissions, it becomes an every year event by about 2080 and thereafter, whereas under a low emissions scenario, it remains like a 1 in 50-year event, so still somewhat rare. So, you know, that's the way in which information can be presented on marine heat waves to better sort of understand what would be like in the future. I also forgot to say, just to remind you, that the causes of these events in the West tend to be, and why this event was called the Ningalo-Nina, is it because they tend to occur during La Nina events when the warm southward flowing Lewin current strengthens, and so it brings more warm water further southwards. The second, the second event is it's a series of two events that affected the the east coast of Tasmania in 2015, 2016 and 2017, 2018. Two different mechanisms for formation. One was sort of like the extension of the Eastern Australian current that led to a very long-standing marine heat wave. It had significant impacts, caused an outbreak of Pacific oyster mortality disease, which strongly impacted the oyster aquaculture industry in eastern Tasmania. It also impacted salmon, captive salmon industry as well. The second event was shorter lived. It was sort of formed by a persistent high pressure system occurring in the east, in the region, but it was quite widespread. And again, a similar story when we look at how frequency, intensity and duration of these events is affected. If we stay on a low emission scenario, these events remain reasonably rare, but high emissions, they become kind of getting down to every year events, which is pretty alarming. This is the case for the 2015-2016 event under a high emission scenario, going from a 1 in 20 year event down to pretty much an every year event from 2080 onwards. Okay, so moving along. Going on to our other fact sheets, we had one that dealt with sea level rise. So in 2019, the IPCC released a special report on oceans and cryosphere. And one of the new pieces, significant pieces of information that came out of that was how Antarctica may respond to ongoing warming, global warming. This has always been a big part of the uncertainty in sea level projections, is how Antarctica is going to respond. And at the time of the last IPCC report, there wasn't enough known about how Antarctica might respond in a dynamical breakdown sense to even put a number in there. So we always were aware that that was a large caveat, that sea levels could be higher than the IPCC range, just because we hadn't factored in dynamical melting of Antarctica at that point. But new science since then was assessed in the IPCC ESCC report and enabled them to come up with an estimate of the Antarctic contribution over the 21st century. So this fact sheet is really sort of saying, well, what does that mean locally? And so what we've done here is we've taken the sea level projections, this is just for one location, Melbourne, from CoastAdapt that we've provided in the past, and these are these horizontal bars showing RCP 2.5, 4.5 and 8.6 at 2100, showing the uncertainty range, the median and the allowance. And for people that aren't sure what the allowance is, it's a way of integrating the uncertainty in the projections together with the median and information on the extremes to come up with a number that's saying this is how high you would need to raise your seawalls or whatever if you want them to afford the same protection in the future under sea level rise as they're giving you now. So if they're giving you some protection from a 1 in 100 year event now, this is how much you need to raise them so that they still give you protection from a 1 in 100 year event in the future. It's just a way of sort of synthesizing all that uncertainty into a single number to stakeholders. But anyway, the key thing here is that under the 2.6 and 4.5 projections, the sea level rise projections don't change much at all from what we had in the past. But under RCP 8.5, that Antarctic dynamic term really kicks in and elevates sea levels roughly 10 centimetres or a little more around the coastline of Australia, depending on where you are. And similarly, the median and the allowance values are equally elevated by about that same magnitude. So it's just giving coastal managers a bit of information about how they perhaps should think about adjusting anything that's predicated on the existing sea level projections, how they're likely to change. Of course, this may change again with the IPCC report due out next year, because there'll be further assessment of the Antarctic dynamic contribution and all other contributions to sea level rise. Extreme sea levels. So we did a little piece on changing frequency of extreme sea levels, and this is really contrasting the difference in reduction in recurrence intervals, similar to the marine heat waves one, that occurs inside a protected harbour versus outside on the open coastline where waves are a significant contributor. And what it's showing is that say a 1 in 50 year event under sea level rise and under all three scenarios, because there's not much divergence between now and 2014 on the different emission scenarios and sea level projections, is that a 50 year event becomes quite rapidly a 1 in 1 year event. On the other hand, where you actually have more, you have higher extremes because you've got more waves contributing, that takes longer to really play out, and there's obviously a much more of a dependency in the emission scenarios. What that's saying is that the 1 in 50 year event inside a protected harbour is actually a much lower event because you don't have the waves contributing. But what that can mean is that those areas can be more vulnerable. You don't have big extremes now, therefore you build a little bit closer to the coast. You've probably, the geomorphology of the region is adapted to a low variability coast water level range, and so it means it doesn't take much sea level rise before you're suddenly starting to experience impacts, whereas an area on the open coast that has a lot more variability is already somewhat adapted to that variability, so it takes more sea level rise to really sort of pack a punch and have an impact. Moving on, we also, there's been a lot of work in understanding what wave climate change means globally, and this case study is focusing on what all of those changes from the Global Intercomparison Project mean for Australia's coastline, and bearing in mind it's not just about the wave height change but also the wave periods and wave directions, because that's what drives impacts along sandy beaches. Small changes in direction, changes in the periods of the waves, long period swell can have more of an impact than short waves, and so on. There can be quite different responses. Probably the take home here is that along the, sorry, I'm just trying to find, here we go. Along the south coast is the area where we're seeing a very consistent change across all climate models for a tendency for both wave period increase and wave height increase, as well as a sort of a slight clockwise, anti-clockwise rotation. So that's sort of meaning these waves, the waves are becoming slightly more southerly from what they currently are. So that's around, the results are only shown on the coastlines where there's a consistent signal of change across a large multi-model ensemble, and the biggest impact really is along the south coast, not surprisingly, because that's where our swell waves come from. And the final little case study is again talking about information that might be useful for the offshore industries, and this is focusing again on, as I've said, they focus a lot on sort of maintenance of their offshore platforms. So how do we provide information that they can use? And this is talking about, well, number of days per year above wave heights of 3 meters, and what we see in Newcastle, which is where this case study is focused, is actually, it's a good news story. Those number of days are going down because the frequency of the typical weather events that cause high waves are actually becoming slightly less frequent in the future. And so that's just sort of showing you how we can tailor information to service that particular community. Okay, so in terms of impact, so that's a little bit of a snapshot of how some of the science that we've been doing. In terms of impact, as I mentioned before, we've had a strong focus on the science, more understanding of the various contributing factors to extremes around the coast. In terms of impact, many papers have been cited or were cited that came out of NEST funded research in the SROC report, and as I've just recently reviewed the IPCC, a couple of chapters in IPCC, I can sort of see they're also being cited there as well. So, that's a bit of impact. We're working very much on mobilising our science through further development of Canute and delivering sort of usable information for our stakeholders in government and industry. We're and also our science has fed into significant reports such as State of the Climate 2020 and so on. We also have some engagement with students through an activity which did take a little bit of a hit last year with COVID, but engaging with school-age students to kind of introduce them to some of the science we do and get them to help. This is through digitisation of old records to try and rehabilitate, data that's sitting there in archives not being used and getting it quality controlled so we can use it. There's also policy and decision making. So, we because of the work we do in the NEST pub, we're often asked to help with helping. We're often asked to help government with questions about do they need to upgrade their planning benchmarks, and we're able to sort of deliver to those kind of requests because of the work we do in the hub. And also the science that we've done has also helped with, for example, framing up other pieces of work, like doing a major study for Port Phillip Bay on coastal hazards. Knowing what we know because of the science we've done helps us to design a project that can really target what we're doing there, which in this case is developing coastal hazard layers. And the example here is wave run-up hazard along the Port Phillip Bay coast. So that's just another example of how our science has impact beyond the actual hub itself. We've also collaborated sort of more widely than inside the hub with other hub activities. So for example, there's a case study on Shark Bay for the World Heritage Advisory Committee to provide projections and expert advice on marine systems and World Heritage values. And so researchers in this hub sort of contributed to that activity. In project 5.3, a couple of several of our hub researchers contributed to a major paper that was assessing CMIP6 models to better understand what's coming down the line towards, for future projections in Australia. Some of the key findings were that there were small improvements in the Australian climate in the CMIP6 models, but generally the results were fairly similar, except for a subset of warm models that had much greater climate sensitivity. Collaboration across with Project 5.8 and Andrew Dowdy was a review paper on East Coast lows, sort of gathering and reviewing all the information, all we know about East Coast lows from the weather, climate and coastal extreme sets of sea level response. So that was a little collaborative activity. And then with Project 5.9, this was a paper that looked at how we can use satellite information to infer long-term changes in shorelines. And the key findings were that, and so this basically chopped up the coastline into 50-metre sort of pixels to try and understand where the coastline was accreting, which is the top figure here, and the colours just indicate whether we're talking about inlets, cliffs, bays, cuspate, forelands, headlands, beaches, and so on. And what you can see, one of the findings is that there's no widespread change. There's lots of very localised change, and quite often where you can have erosion, accretion somewhere, you can have erosion just slightly down the shoreline. So, these tidal inlets were found to be the most active in terms of change, perhaps not surprisingly, because there's a lot going on in tidal estuaries and so on. But this just kind of provides a bit of a snapshot of how satellite imagery can be used to try and infer coastal change. Yeah, so I'm nearly finished before I hand over to Julian, but looking ahead, there's still obviously, we still want to maintain and continue to analyse our historical data sets to monitor changing trends. There's still work to be done in that area, looking at waves and coastal extremes. Continuing to lengthen data sets through digitisation activities is an important piece in what we want to continue doing. Updating models to produce more improved hindcasts and future projections of sea level, waves, coastal extremes, and further analysis, I should have put in there, of marine heat waves and so on. Analysing model information to understand linkages of, between the various extremes and modes of climate variability, so we can kind of tease apart the different contributing factors when we're trying to understand likelihoods and probabilities of extremes. Continuing to develop functionality and tools so we can deliver this information to our stakeholders, and increasing community and stakeholder knowledge and awareness of coastal sea levels, waves and extremes and their projected changes. So on that note, I'm going to hand over to Julian to take over and talk us through some of the information that's out there on our website and in the tool itself. So over to you, Julian.
Okay. Yep, thanks for that great science and the work summary. I guess I'll be talking about where we can find all the data and the information behind this, and what we put on our sea level waves and coastal extreme website, and also how we can sort of interact with the data for extreme sea levels through the Canute web tool. So this is really focused information on the coastal extremes and marines. There is also information that you can find on the NESP Hub website. Okay, apologies. So this is our website that we have that looks at coastal sea levels, waves, and coastal streams. So on the left is the top part of the web page when you click on the link, and I think the link's been popped in the chat site if you want to have a look. And this is the bottom showing our website broken up into the various categories of sea level, waves, extremes, energy, and also the people in the group. So if you look at the sea level section, there's a huge amount of information, data and content about understanding past sea levels and improving projections for the future. So there's information on why sea level changes, past sea level, future sea level, and how we measure the data and where to get the data. And on the right here, this is the long-term data set. So the long-term being, the measurements through over the last 500 years, but also tide gauges over the last 100 years and over the last decade of the satellite era. But so also there's content on our wave analysis that Kathy was talking about. So the GCM forced wave climates, looking at the future climate through the CalClip project. So links to the CalClip project and the data sets where you can access the data here on the right and download it. And you can also find information on publications and people. So these are the people that have been working in 5.8 and also the associates that are from the larger 5.8 that have been working on the project. And there's information on extremes. So Kathy was talking about the tide gauge digitization. There's a bit of information that you can go into the website and find more information about how we're doing that. And the Canute tool is contained within our own website, where you can look at previous Canute, the history of Canute, which was started by John Hunter at the University of Tasmania, and he's retired, and how we've taken it up and we've built Canute 3 and improved it over time. So what is Canute? Canute is I would call it a sea level calculator, where we can interact and look at what sea levels are around the coast of Australia. So how high the water level gets during extreme events depends on where you are at the coast. So out in the ocean, we have satellites. They're measuring mean sea level, so we get an idea of how sea level changes generally in the ocean. But when you get towards the coast, wind and inverse barometer effects on the shelf will increase sea levels due to storm tide. So in protected harbours where there's no wave effects, we can measure that effect of storm surge through tide gauges. So we get an idea of what the storm tide is. So important for large scale coastal inundation. On sandy beaches exposed to higher waves, cameras look at the beach, and we've been able to measure how far up the beach sort of waves can run, and we can then from those measurements extrapolate what an extreme event might look like from offshore wave conditions. So this is when you open up the link, which again is in the chat, we can see the Canute website. There's a whole lot of functions to control what we're showing on the left, and on the right we open up to a map tab where we see the map of Australia. There's other tabs to look at the data output, and also a help tab to find more information. So the map is zoomable and clickable, so we can zoom in. So this is zooming into the Sydney Northern Beaches area, showing model output points of what the extreme sea levels might be. So we can choose a point to investigate what extreme sea levels might be. We can also select beaches. So that was just looking at model output of storm tide, but we can look for individual beaches. What's the included effect of waves? So dangerous surf as it goes up against the coast increases the time average water level. We can have a look at what the impact and how high the sea level will get there, as well as just look at the tide gauge, the measured sea level, just as a reference to see what the model on the coast looks like in comparison. So once we click on a point, we accept a disclaimer, and we can plot it. The tool allows you to plot it in different ways. So here we're plotting how high the water level is for different annual exceedance probabilities, the probability of it being exceeded in any given year, one being 100%, or we can plot it as a return level period, which is default. Here we're plotting up the tide gauge along with different model estimates of what the extreme sea level return level heights would be. And below is a table of the data. So the table of the data provides the data for different greenhouse gas scenarios and climate model ensemble percentiles that you select here. Here is a drag box for choosing a future year that you want to investigate. So you select it out, and then you'll see a new lines that indicate what the future sea level rise will be based on tidal, and we can see that it tells information about how high the sea level might increase in table, but you can graphically see that something like a 1 in 500 year event will now occur much more frequently, more often than once a year with this amount of sea level rise. But we can also select beaches. That was just for a tide gauge example, what would happen inside a tide gauge. But if you select a beach, we can now also look at the impact of waves. So this top plot shows the wave setup, and this shows the total water level, including the wave setup, for two different equations for estimating wave setup. For more information on wave setup, you can click on these links, and there's general guidance on sea level rise and the allowance in Canute, as well as wave setup and extreme sea levels. There's links to the Coast Stat website for this local council, the Pittwater Council, Surf Lifesaving Australia, information about the beach, Narrabeen Collaroy on the northern beaches, and Climate Change Australia to look at other marine climate extremes, and the coastal risk. So if we pull out an extreme sea level, we can go into the coastal risk, and we can look more at what the inundation might be around this location, which you're welcome to play around with. So a new feature that we've recently put into Canute is to look at how so this plot here shows how a design storm, a 1 in 100 year event, for example, might change over time for different RCP scenarios. So here you can select a data set. So this is storm tide plus the wave setup, so what you'd expect on a beach. And Kathy was talking about this before, how extreme sea levels will change in frequency. So a 1 in 100 year event might become a 1 in 1 year event for a high emission scenario, before 2080, when you consider beach. But when we now look at just the storm tide, which would experience inside protected harbour, we can see that it's occurring much more frequently for the reasons Kathy explained. But the exposure to waves makes the protection from waves means that the protected harbour hasn't experienced larger variation in sea levels. And all this information about Canute is provided in the help tab, as well as the case study walkthrough that I'm presenting right now. So you can click there and go through that. So we continue to improve Canute and the science behind it to include information. So Canute really just talks about changes in mean sea level and how that will impact extreme sea levels. But I guess what we're interested in is what will happen with future changes to wave heights. How will they impact extreme sea levels? Will they do that in the same way? So we've got a talk at AMOS on Monday. Well, I've got a talk on Monday talking about, in session 8.4 after lunch, talking about how waves are changing around Australia from the GCM force climate projections, the CalClip ensemble. Okay, so leave it there and hand back to Sonia.
Great. Thanks, Julian and Kathy. Thanks so much for a really informative talk outlining all the science achievements achieved under your project under the Hub.